There we go. All right. So again, we are concerned about lead levels in water. And here we have an old elementary school, and we want to see if there's more than 15 parts per billion of lead. And we have a sample of 50 vials of water. And we want to know if this sample significantly exceeds. Okay, so significantly exceeds means greater than, true? Greater than must be an alternative hypothesis. So that right there is giving me the alternative. Here they say no more than. What does no more mean? It means less than or equal to. That's got to be the null hypothesis. Okay, so this statement right here is giving me the null. This one right here is giving me the alternative. So new situation. So we are looking at average lead in drinking water measured in parts per billion. So you should write down what the parameter is. PPB. And then our null hypothesis, H0, that's supposed to be a colon there, I believe, is mu, because I'm talking about a mean, and the null always has to talk about the population, not the sample, is it can't be more than, so that it translates as less than or equal to, and they give 15 as the value. So that should be the null hypothesis. The alternative hypothesis is that we don't want it to exceed that. So mu is, we're checking to see if it actually does. Is mu greater? Okay. Does this sample this set of samples significantly exceed? Significance level, 5%. Now this is children's health, so we might lower it, but I'm just going to go with the 5%. So alpha, we're going to go with the typical 0.05, which is 5%. All right, so that's our setup. We have to state what our parameter means. So that's in my own words what the parameter is. Average lead parts per billion of drinking water. And then I gotta have some information about the null and alternative hypothesis. State that in symbols. Okay. Once I have that, then I grab the sample and try to run the hypothesis test. And we have like 7 steps to make that happen. All right, so part 2, I would like you to go grab that data set, copy the 50 values of lead in the water, and take it over to STAT243. Okay, which type of hypothesis test are we running here? Yeah, it's a single mean, so that's the one we're going to pick. And then you're going to edit your data in there. You're going to adjust the null hypothesis. You're going to generate samples. You're going to pick your test. And then you're going to plug in your sample value. All right, give it a shot. I'm going to pause for a minute while you get that set up. All right, so here we go. So ultimately, I want to address all this stuff here. In particular, our current goal is to get the p-value. And if you forgot how to get a p-value, I've got these summaries of how to do it. So just going to refer back to this. So I need to go to STAT243, single mean, edit in my data, set the hypothesis value. All right, so let's do that. So I've got data linked from here, and I've got it copied. And then I got to run over to STAT243, make sure I'm on the right page. Hypothesis test single mean. All right, edit. Control A, delete, paste. Got a header, so the buttons are correct. Change, don't forget to change the null hypothesis, super important. EPA says 15. And then once I have the data and the null, then I can start generating. All right, I got 6,000 new samples, each of size 50, and these are all the averages of those samples. So if this sample is representative of water at the school, then other samples of 50 could have an average as high as like 18-ish or as low as 12-ish. Okay. What do I do next? Well, next I have to pick the test I want. And since that's a greater than is to the right, that means a right tail test. The alternative hypothesis always tells you what test. Okay, so right tail. And then I plug in my sample mean. So down here, I'm going to drop in the 16.5. And once I do that, the number above is my p-value. Okay, so we're getting p-values a little above, a little below. Somebody got at 0.05. All right, so I'm going to make a quick sketch of that. Oops. So my sample, make a slight note to the side there, has n equals 50 things in it. It's got a mean of 16.5. And graphing that, so what StatKey does is StatKey gives us a scale on the axis here to show how far apart 15 and 16.5 are given the sample size. So mu equals 15 is the middle of my distribution, and 16.5 is kind of far out to the right, not way out there like the previous one we did, right? So that would be, I'm guessing, about here-ish. So that's x bar equals 16.5. And then StatKey says other possible samples to the right of that mean could be, what was mine? 5.something%, 5.3%, 0.053. And so that number above is the p-value. The p-value is about 0.053, which translates as 5.3%. So I got my p-value. So next I'm going to state what the p-value means, then I'm going to use that to make the decision, and then I'm going to use that to write the conclusion, and then I want to talk about the significance of that practically. And what if I made a mistake here? Now, some of you have a different p-value than me, right? Some of you have a p-value of 0.04 something. Yours is below the threshold, which means you would make a different decision than me. That happens. All right, so next, let's interpret the p-value. And to do that, I'm going to refer back to some stuff we learned about probability, because the p-value is a kind of probability. It's a conditional probability. So it's the in statistics notation, probability notation, it's the p probability that a sample mean is more than my sample mean given, remember that vertical bar for given or if with conditional probabilities? I was expecting the population average to be about 15. In words, there is a 5.3% chance of finding another sample with a mean greater than 16.5 parts per billion of lead, given that we were expecting a mean of 15 parts per billion of lead. So the p-value is the probability of having another sample with a more extreme value than our sample when we were expecting it to behave like the population. That interpretation is of minor importance to me. What's more important is that you know how to get a p-value, and then you have to know how to use the p-value to make a decision and a conclusion, which are the next things we're going to do. All right, so next thing we need to do is come up with our decision. So to make a decision, you have two possible decisions. One is reject the null hypothesis, or fail to reject. The null hypothesis. And we make those decisions based on comparing the p-value to the significance level. So if the p-value is less than the significance level, we reject the null. If the p-value is greater than, or say equal to, alpha, then we will fail to reject. Now, some of you got a p-value that was less, so you get to reject the null. My p-value is not less, so for me, because I have a 0.053 versus a 0.05, mine is greater, right? I am failing to reject the null. After we have a decision, we need a conclusion. And the conclusion is either if you reject the null, that means you have evidence to support the alternative. Or evidence does not support the alternative. My hypothesis test, since I came up with a bigger p-value, right, I'm in the right column here. My evidence does not support the alternative because I failed to reject the null because my p-value is too high. What that means is it's close enough to 15 parts per billion given the sample size. When I get a conclusion from you, this is a generic conclusion. That's not what I want. I want it in context. Given what the alternative means in this situation, I want you to tell me what there is or is not evidence of. So I'm going to pause again, and I want you to look back at what we said our hypotheses were and state what we do or do not have evidence from. And again, some of you do have evidence of it. Some of you do not. Depends on your p-value. So make your best statements for this particular situation. What is this alternative hypothesis? What is it that we have evidence or don't have evidence of? All right, go. Write something down. Don't worry about being wrong. You're going to get to correct it in a minute if you don't get it quite right. Start writing down. Resume recording in a minute. All right, so again, these are the possible things that can happen when we make these decisions. Either we reject the null or we fail to reject the null. And then the reality that we really don't know about, because we just have a small glimpse of what that reality might be. And either the null was true or the null was false. And if we put those two things together, we get 4 possible outcomes. 2 of them are good. Right? Cool, that's a good thing. That's a good thing. And 2 of them are errors in the decision. And type 1 error is when we reject the null, support the alternative, but the null was really, population is really what the null said it was. Alternatively, we could fail to reject, but the null was false. And again, that's another error in the decision process. Now, practically, let's think about this now. So I just want to look back here at my sketch. Here we go. Is the average amount of lead in this sample higher than what the EPA says it should be? Yes, it is. Now, my hypothesis test said it's not significantly higher. Okay, so this has statistical significance. It's not high. However, practically, looks like more than half the samples are above 15. Practically, this is a problem, even though statistically it is not. So even though my hypothesis says, nah, it's close enough, there's still more than half the samples that are over. So I really got to tell the school board, practical significance is you have a lead problem. So you should deal with it.
Would the way to address that be to adjust the alpha value?
Yeah, you could drop it down, right? So if, like I said earlier, public health concerns, I might make the chance of making that type 1 error lower. And in this case, that also lowers the chance of making the type 2 error sometimes. And then here I can say, all right, we better, well, oh wait, I just said, okay, hang on. I don't think I said that right. Stop, rewind. If we lower, yeah, no, so in this case, with the kind of error I was about to make, the alpha is not going to help. It's the other probability which of making the type 2 error, which we can't easily estimate, is a problem. So lowering that will not help me change the outcome I just had. So scratch that. But again, the practical significance here is that there are a bunch of samples, more than half, that have too much lead in them. So it doesn't matter what the average is. There are many samples that were too high, so we got to address that. Okay. But there are other situations where you find they're far apart, but who cares? It doesn't really change anything. Right. So sometimes there isn't practical significance when there is statistical significance. Sometimes there is practical significance, even though the statistic says, no, they're close enough. But again, that's a judgment call. So sometimes these tests give us definitive things to say about it. Sometimes they don't. All right, let's do another problem.